So thank you, Ale. And yeah, as anticipated, again, I'm glad for the ICOSES committee to propose to, arrange this soiling workshop. The real aim, again, of this event is to, again, talk a bit about also not just status and challenges, as you can see from the title, but also the resources that are available to model soiling. I'm very glad today because we have some of the main experts in soiling being able to talk with you today about different aspects related with soiling accumulation as well as soiling mitigation. Again, I'm Leonardo Micheli from Sapienza University of Rome. Ale will be co-moderating the session with me, which will be consisting of 4 different presentations and then some time for some Q and A. Ali, I'm not sure if you want to add something.
No, I think we are already 3 minutes ahead, so we can start. Go ahead.
Okay,
thank you.
That is good. So our first presenter is Álvaro Fernández Solas from from DLR in Germany, actually located in Almeria in southern Spain. Hi, Alvaro. Thanks for joining. So Alvaro is an industrial engineer, also a researcher. Right now, he mainly works in the topic of agrivoltaics, but he has built some experience and a very good track record also working on soiling. Over the years, his work has included, for example, soiling modeling, photovoltaic modeling in general, as well as O&M optimization. He is a good, excellent Python user, has also experience with MATLAB and LabVIEW. Is also right now also coordinating and managing successful research projects, and he has a PhD from the University of Jaén. So, and he's gonna give us today an introduction to soiling and to soiling modeling approaches. So, Álvaro, the floor is yours.
Okay. Thank you very much, Leo, for the kind introduction, and thank you all the organizing committee for inviting me, for allowing me to be here. So I'm going to share my screen. I'm going to start directly. Okay, so now you should be able to see my screen in full mode, right?
Yeah, we see the screen. We hear you well, so go on.
Okay. So yeah, as Leo said, I will kick off the workshop with an introduction to soiling and modeling approaches for PV system. So here you can find the agenda of today's presentation. So I will start with some basic but essential concepts to understand the issue of soiling in PV system, and then I will move forward to the different modeling approaches. So I wanted to start this presentation with these 2 pictures. If you attended the previous talk by Leo, you already are a bit familiar with them. So we can here see the effect of a dust storm in a city in Spain, Almeria, southern Spain, and then the consequences after the dust storm with the accumulation of soiling of particles on the PV module surface. So let's start with the definition and impact of soiling. So basically, soiling is the accumulation of different particles, which can be dust, sand, or bird drops on the surface of PV modules. You can see here in the picture different types of soiling. And soiling reduces basically the energy production of PV system, but it also increases the operation and maintenance costs, and it also leads to higher uncertainty on the prediction of the PV energy production. So basically, soiling absorbs, reflects, and scatters part of the incoming light, and therefore it reduces the effective irradiance that can reach the cells of PV modules. We know that soil accumulation can depend on many factors, such as those related with the characteristics of the site, the PV system configuration, and even the type of the PV module. Soiling is also driven by different physical mechanisms, such as rain, wind, as was mentioned before, that can affect both the position or removal of soiling. The economic losses in the PV sector associated to soiling are not negligible at all, as we can see here in this plot. For example, in 2018, it was estimated that soiling reduced the global PV energy production by at least 4%, with annual revenue losses of at least 3 billion euros. For 2023, losses between 4 and 6.5 billion euros were forecasted by a report. However, a recent update suggested that the losses could have been even notably higher, up to 8.5 billion euros. For 2026, some scenarios forecast global soiling losses that can be higher than 10 billion euros. So soiling is a big issue in the PV sector and should be, of course, considered. In order to quantify soiling, it's important to know which indicators are typically used. So the most common one is the soiling ratio, which is already defined in the IEC standard. So basically, soiling ratio correlates the electrical outputs of a soil PV device and the same device in clean conditions. When the soiling ratio has a value of 1, it means that there are no soiling losses, so both devices are clean. And the lower its value, the higher the soiling loss is. So the soiling loss is 1 minus the soiling ratio. Then we also have the soiling rate, which represents the daily rate of change in the soiling ratio during accumulation periods. We can see here in the plot 3 different accumulation periods with different soiling rates. But in some desert sites, soiling rates of up to 2.5% per day have been observed. In the next slide, I want to highlight that soiling is not a problem only associated to arid regions, as Leo mentioned already before, but it's a global issue. And so I will start here with some myths about soiling of PV system. The first one is that rain cleans the modules in an effective way. So this is something that most people still think, but unfortunately, this is not totally true. And artificial or professional cleanings are still required for the majority of the PV system in the world. The second myth is that a single cleaning per year, typically in summer, could be enough, could be sufficient. That's not true, as soiling accumulation can vary throughout the year. For example, if we have these dust storms, for that reason, cleaning schedule should be optimized to the current condition. And the third one is that clipping losses completely eliminate soiling losses. We know that soiling reduces power generation before clipping even occurs. For more details about clipping, Leo is going to talk about it in the last presentation of this workshop, so don't miss it. Focusing a bit now on Europe. Here in Europe, especially in Central and Northern Europe, the impact of soiling has been overlooked, as rainy locations were considered soiling-free. However, fortunately, this is changing, which can be reflected in the major interest from the PV community in soiling effects and their mitigation. So here, in these two plots, we can see 2 examples of this enhanced interest in the topic. So the plot on the left validates the performance of 2 different PV soiling models, which I'm going to explain a bit later, against actual measurements in an urban location in central Spain, with soiling losses close to 9% in spring and summer. On the right plot, we can see the performance ratio profile of a site in Switzerland close to a railway station with important soiling losses, up to 10%. And this site with really high and really frequent precipitation clearly presents an evidence and refutes the hypothesis of rain cleaning PV modules in an effective way. The second point, Leo already mentioned, I explained and talked a lot about it, is the consequences of Saharan dust intrusions over Europe, dust storms, which have become more frequent and intense in the last decades. So here we can see the one dust storm that affected most of Europe 3 years ago in March. And here on the right, we can see they also presented this plot before, the impact of two different dust events on the soiling ratio profile on a PV plant in Portugal. Moving forward to research, the interest in soiling related topics has gained a lot of traction in the last 15 years with an exponential growth in the number of publications. Taking a look to the origin of these publications, we can see a relevant number of contributions from the MENA region, with at least 5 countries in the top 11, being Morocco in the top 9 position, but also countries where soiling was typically considered not a problem, like the UK and Germany, are actively conducting research on the topic. In this workshop, we are going to cover different lines of research. We are starting now with the modeling of the PV losses, which you can follow here, and also in the following presentation that will be given by Tore Müller, who will present a recently launched Python tool to calculate and to easily model soiling. Then the topic of soiling monitoring and quantification will be covered by the presentation of Fabian Borferstetter. And then the last talk, Leo Micheli will speak about the topic of soiling mitigation and will also cover some economic aspects. So now let's go into more detail about soiling modeling. So in the following slides, I will try to answer these 3 questions. So is it possible to estimate soiling losses before the deployment of a PV system? Which models are currently being developed and are now available for soiling estimation? And I'm going to briefly explain the inputs, the methodology, the complexity, and the outputs of some soiling models. So here we can see the different approaches that I will introduce in this presentation. So we have environmental based and physical models. We also have machine learning model. And lastly, I will present also some estimation of soil losses from measured PV performance data. So starting with environmental based and physical models, and the good point of this model is that they make it possible to know the impact of soiling at a site even before the deployment of the PV installation. Basically, this model consists in the following 3 steps. So the first one is the analysis of environmental parameters and PV system configuration. Then these models calculate the accumulated mass density on the models, and finally, through some empirical equation, they obtain the electrical solid losses. Here we can find in this list the most widely used soiling models based on environmental parameters and physical equations. I'm going to go into more detail now. So here in this table, basically I summarize the main characteristics, the required inputs, and the limitation of the different models. So as you can see here in this column, they cover different levels of complexity and can require more or less inputs. But some common limitation of all of them is that they consider rain as a cleaning agent. I will go further into this topic in a few minutes. Most of them also, or all of them, require a specific local calibration for a better performance and agreement with actual measured data. And 2 of them, which I'm going to explain a bit more detail now, are already implemented in PVL, so they are really easy to implement and to use in your application. Tori is also going to mention at least one of them during his talk, which are the Kimber model and the Coelho or the HSU model. Starting with the Kimber or the fixed rate precipitation model, and this was the first soiling model to be developed almost 20 years ago in 2006. The main limitation of this model is that it only considers rain as a responsible of soiling cleaning if the accumulated daily precipitation is higher than a certain threshold that the user can specify. So there is not a universal threshold that we can follow. So here in the plot, you can see an example of the application of this model for soiling modeling, considering a cleaning threshold of 5 millimeters of rain per day and a soiling rate of 0.15% per day. This is also a limitation of the model, as the user should know more or less which is the average soiling rate in a certain location. So some examples of this limitation, or the limitation of the model, is that by considering different soiling rates but keeping constant the fixed cleaning threshold, we can appreciate in this plot the differences between the different choices. So we can appreciate that there is a linear relationship between the soiling rate that we can choose, or we choose, and the average loss. So it's linear. The higher the soiling rate, the higher the soiling loss. And this is something that it depends on the user. There is no guideline about the soiling rate that we should choose. The same, but in this case, considering different cleaning threshold and keeping constant the soiling rate. So we can see how the use of different cleaning threshold impacts the soiling profile and the average soiling loss. A bit different. In this case, the relationship is not linear, but still, the higher the cleaning threshold we use, the higher will be the soiling loss that our model is going to deliver, to provide us output. Going now, moving forward to the other model, to Coelho model. This is also a widely used model, and it's also implemented in PVLib. It was developed by Coelho, a person in the US, and it basically considers, in this case, both particulate matter concentration and precipitation intensity as drivers of soiling accumulation and removal in the case of precipitation. Again, the main drawback of this model is that it assumes that a day with a precipitation higher than a threshold restores the soiling loss to zero. And as I said, rain shouldn't be considered a perfect cleaning agent, and the use of this threshold maybe is not the best approach to model soiling removal, as there are also other factors that affect soiling removal in this case. So we can see the equation here. This is an empirical equation, and basically the Coelho model correlates the accumulated mass density on PV modules calculated by using different setting velocities as a function of the diameter of the particulates with this electrical soiling loss. It's already implemented in PVLib, and you can follow some examples, and Tori is also going to present some results after this talk. Here, I'm conducting again similar example as I did for Kimber model, but in this case, I'm considering different values of the position velocities. So we can see how the choice of these values affect the soiling profile and the estimated loss. We can appreciate in the plot how the peak soiling values here can range between 2% and 12% for deposition velocities between 0.1 and 1 centimeter per second. So there is a huge difference depending on the value we choose. As I said, rain is not a perfect cleaning agent, so we work on that. And in order to assess the completeness of cleaning due to rain, we introduce a new parameter into Coelho's model, which we call the cleaning factor. This factor basically indicates the fraction of accumulated mass that rain can wash off. So in this plot, we evaluate the impact of this new parameter when applied with a value of 0.2, which means that only 20% of the accumulated mass is washed off or can be washed off after a rain event higher than a threshold. In this case, the threshold, we set the threshold to 5 millimeters. This is represented in the soiling profile by the red line, and the green line will be the baseline scenario. So we can see that there is a significant difference with average soil loss that is almost the double of the soil loss in the baseline scenario for a site in southern Spain, in Almeria. Here, these soiling maps of Europe also represent an application of sample of this modified version of the model. So in the perfect clean scenario, the average soiling loss in Europe reaches a value of only 1%, while this average loss increases up to 5.3% with a 10% partial clean scenario, considering a clean factor of only 0.1, 10%. So comparing both maps, we can appreciate how soiling losses can reach non-negligible values, higher than 6% in Central Europe if we consider this partial cleaning by rain. So it should be something that may be evaluated in future works. How can we optimize this cleaning factor parameter? Because maybe it's not 10%, but for sure it's not 100%. Rain is not a perfect cleaning agent, but probably it's either not 10%. So we should continue studying which could be an effective cleaning factor value for different sites in the world. Another approach of soil modeling consists in using machine learning models. So these models basically appear as an alternative to physical models and can be useful when access to on-site measure environmental data is not possible. As can be seen here in this figure, they are not better than physical models when trained with field observation, but they are a solution, as I said, when we don't have access to field observation. And if we are using satellite-derived data, maybe it could be an option to consider. Maybe they should be further developed in the next few years. Another application of machine learning is the modeling of the cleaning effect by rain, which has been conducted by my colleagues here at DLR to address one of the principal assumptions of the currently available models, which I already mentioned several times in this talk, which is the use of this threshold approach to consider a perfect cleaning effect by rain. So my colleagues corroborated with soiling data from multiple sites in Africa that rain only has a partial cleaning effect. So they tested two different machine learning models, a linear regression model and the random forest model, and compared the results against the typical threshold approach, considering 1 millimeter as threshold. And they also validated the simulation with data from more than 30 soiling stations in Africa. They found that the calculated error matrix demonstrated that the linear regression and the random forest models outperform the threshold approach, while the lowest error metrics were provided by the linear regression model. We can see here in the table the values. Both of the statistical learning models outperform the typically used threshold approach. Zooming in on the left bottom side of the plot, we can see that the threshold approach underestimates the soil loss recovery in many cases, but it also overestimates it in others. So there is not a clear pattern. Also, they observed that no model captured well those rain events that increased the soil loss. So for example, in the case of red rain, we can have even an increase of soil losses and not a recovery. Lastly, these machine learning models can also be applied for soil forecasting. So making prediction based on historical information. In this plot, we can see the results of one of these models, which systematically adjusts the coefficients of a linear model based on the previous estimation error and the soil loss on the day before, which errors below 3%. So the results were quite good in this case, from site in Madrid, Spain. Lastly, the last approach that I want to highlight today is the estimation of the soil losses through PV performance data. So I'm going to describe two different models or approaches. The first one is the stochastic rate and recovery method, which follows 4 different steps. The first one is the application of different filters to the raw PV performance data. So basically to consider only central hours of the day, mostly around noon, 2 hours around noon, and also only high plane of array irradiance value, higher than 500, in some cases 700, depending on the accuracy you want, on the type of on the site. Then the second step is the detection of cleaning events, basically to split the data set into different soiling intervals. So we can see here in the plot how by detecting different cleaning events, it is possible to divide the data set into different periods. And finally, the soiling rate, the slope of each interval can be calculated. And by conducting Monte Carlo simulations, it is possible to generate multiple profiles and then calculate the soil losses. The second method, and as an alternative to the soiling rate and recovery method, is the modeling of the soiling profile through change point detections. So in this case, the data set is divided into segments by identifying cleanings or change points in the PV profile. You can see here in the plot how change points are identified, basically cleanings here. And then linear regression fits are applied to each of the periods to calculate the slope or the soiling rate. Coming to the end of the presentation, so I will conclude with some remarks. So basically, soiling is a really important topic within the PV field and should not be underestimated, as soiling can cause not negligible soil losses, energy losses. Soiling is a global issue. Leo mentioned that with the impact of dust storms in Europe and in different parts of the world, and it's not restricted to arid, deserted or dry regions. Rain isn't always a good solution, and models need to reflect that. And we also know that right now, soiling models based on physical equation and environmental parameters are still the most popular, but there are efforts to develop machine learning models and other approaches that can complement the traditional physical-based models. And it's also important to mention that modeling should be a complement for soiling monitoring. So without soiling monitoring, it's not possible to further develop soiling models. So it's really important to have also a proper soiling monitoring solutions in the field. As I said, rainfall alone should not be considered, and the only mechanism responsible of cleaning, of soiling removal. There was a question before about wind. Of course, wind should be considered. The topic of soiling modeling is not simple, and there are multiple environmental factors that can impact both accumulation of removal. Yeah, lastly, I would like to emphasize again that soiling models should be used alongside monitoring approaches to support this ongoing model development and adaptation to different climates, different PV system configuration like agrivoltaics, floating, building integrated, etc. So thank you very much for your attention, and I am open to any question you may want to ask. Thank you.
Thank you so much, Alvaro, for really the great overview. Really appreciated that you highlighted both the status as well as the ongoing challenges, right, with the topic of modeling. I see a raised hand.
Yes.
Yeah, go ahead, please.
Okay, thank you very much for the very interesting presentation. I introduce myself. I'm Professor Zinb Akhshmal from Qadiriyat University in Marrakesh, in Morocco. It was very, very interesting for me. And I have a question about the coatings, please. If Dr. Alvaro Fernandez could highlight the most promising anti-soiling coatings in development and their scalability for utility scale solar farms, please.
Okay. Thank you for your question. I mean, soiling coatings are an important topic within the field of soiling in PV system. It's a bit out of the scope, but I think that, just Leo explained in the previous talk, soiling coatings are being continuously developed, different coatings, and tested into laboratory environments. And I think the main challenge right now is to apply these coatings into, or to manufacture these soiling coatings in large scale. So large quantities of coatings and apply them in real large scale PV installation around the world to test their benefits to mitigate soiling impact. Regarding modeling, soiling modeling, it could be also an important point to take into account the effectiveness of these coatings within the model. So this is a point that if the topic of developing soiling coatings further developed, should be included in the models, how the efficiency of soiling coatings can be somehow included in modeling soiling. Yeah.
Okay, thank you. My question was like if the continuity of another point of my question is like if you are considering this coating within DLR, if you are if you want to use them, because for us we are working in materials here in Marrakesh. And for us, it's a very important topic. This is why I'm trying to make a synergy between what we are doing and what you are doing. This is it's okay.
Yeah, I'm not working on that part, but some of my colleagues at DLR are working on coatings development, and some, I think there are some, or they had some projects in the past about developing anti-soiling coatings. So this is a topic that we are working on here at DLR in Almeria, Spain.
Okay, thank you very much.
Alvaro, there
Hello?
were...
Hello?
Yes.
Leonardo, hello everyone. I just have a question, if you allow me, please. I couldn't raise my hand.
Yeah, go ahead, Butcher.
Okay, thank you. Thank you, Alvaro, for your nice presentation and very informative. So I just have a question, like, do you think, are we close or far away from finding or having that universal model that will model soiling and work for everyone and in all environments? What do you think about this, considering your experience in this field?
Yeah. Thank you for your question. It's a really good point. I think we are still a bit far from reaching that point, having a universal soiling model that is valid for all sites. I mean, as I said, soiling in PV could seem a simple topic, but when you start investigating about it, you realize that modeling the impacts, it's really challenging, and there are so many factors that can affect not only soiling deposition but soiling removal. So I think we are still far from reaching that point, but hopefully there are still a lot of efforts already ongoing, and we should be at least closer in the next few years.
Okay, so there is much like work to do.
Yeah, there is still work to do.
Okay, so do you have any like critical recommendation that, for For example, you say, we should have these things, otherwise we will not achieve that universal model?
I think one important point that there have been already some efforts in the past, but we need to identify which parameters affect most soil accumulation and soil removal. By knowing these parameters into more detail, we can maybe analyze better how they impact soiling and the different patterns of soil accumulation. And maybe another point could be to consider different dust types, so characterizing the optical properties of soiling. I think those two topics are key to enhance the development of soiling models.
Okay, I
Thank
see.
you.
Okay, thank you very much for your answer.
Thank you,
Leonardo.
Buchera. Thank you, Alvaro, for the great presentation. There is a lot of questions. I'm very sorry we cannot answer yet, all of them. I see a few of them in the chat. There is one also in the Q&A. I see a few raised hands. Please write your questions in the Q&A tab, and we will have time at the end of the other presentations to ask additional questions to the speakers. So thanks again, Alvaro, for your great presentation. Thanks for accepting to be here. And we move forward to our next speaker, which is Tore Müller from PV Radar, Germany. Actually, Tore is the CEO of PV Radar company that he co-founded now a few years ago. He actually has some hands-on experience on soiling and photovoltaic in general, and right now he works as again as CEO, Chief Executive Officer as PV Radar, a software platform for transparent assessment of climate-related performance losses, optimization and mitigation strategies, and modeling of economic scenarios. So they've been doing some great R&D over the past month. So if Tore is online, I will give him the floor.
I'm here. Hello, Leo. Thank you very much for
Hey,
the
ciao,
kind
Tore.
introduction. Let me just check. So yeah, I will share my screen. Can I share the entire screen? Because I will. Okay, well, thank you very much, Leo, for the introduction. Yeah, and thank you, Alvaro, for introducing the topic and giving a very nice overview about the current state of soiling modeling. What I would like to do today is, besides quickly introducing of who we are and what we do, I would like to show you a new Python package that we have been developing, which is basically allowing anybody to perform soiling modeling very easily and do much of what Alvaro, for example, has been showing. So I will be doing something a little bit different today. There will be a live coding session where we'll just show you how quickly and easy you can model soiling and understand its effect on PV power plant production. But before I'm getting ahead of myself, so let me first introduce who we are. All right. Oh, yeah, sorry, this was the slide. So yeah, I will give a short introduction about who we are, do the live coding session. I will also show you then at the end how you can start using the PV Radar Python package yourself. It is free to use, so anybody is invited to use it for their soiling modeling projects or any other modeling, to be fair. And then of course we have the Q&A session. Right. So introducing the team behind PV Radar Labs. So we are a company, we're a consulting and software company mostly that specializes in the modeling of complex phenomena in the PV sector. So for example, soiling, cleaning, we do soiling assessment, cleaning optimization, and other things more. Yeah, and what we are proud of is that we're very close to research. We have always been, and this also is reflected in our advisors, one of them being Leonardo Micheli. Thank you very much for your support since the early days of PV Radar. Right, we're also part of the IEA PVPS Workgroup 13. So yeah, a lot of basically what we want to do is bridge the gap between research and the PV industry, and make research available to the PV industry in a very convenient way. Just to give you an overview about the kind of things we're doing. So our interest doesn't stop at soiling. We do soiling estimation. We have developed our own soiling model. So there was the question of that universal soiling model. There was also some interesting aspects mentioned by Alvaro, introducing a sub-unity cleaning threshold. So these are the kind of things that we're also doing, and that we have introduced in our own PV radar soiling model, which is not public, but it is available. Well, we can make it available. We have been working a lot on validation of soiling models, building a database of soiling measurements that we can use to fine-tune parameters. We're very strong in cleaning optimization, having built a platform that allows people to just compare robots and tractors and manual cleaning for any location and any type of design, and then come up with an optimal cleaning strategy. We're also looking into snow modeling, and then there are other fields of interest like curtailment and clipping, and now batteries. So any complex simulation question that comes up that is not really covered by, let's say, PVSys yet. This is the kind of things that we look into. And below you see some examples of the work we have been doing, and you will find more on our website. I won't go more into detail than that. What I want to talk about today is what I want to talk about today is the sorry, I'm just moving. Okay. What I want to talk about today is our Python package that we have. So basically the idea is, so over the past 3 years that PV radar exists, what we have learned is that, well, of course, we try to solve the soiling problem by modeling, but then we realized that there's already a lot of good research out. There's a lot of great researchers, there's a lot of great professionals that have a lot of knowledge about this, and they all struggle with the same problems, let's say, that we struggled with: getting the data for any location, getting the PM2.5 and PM10 data to run an HSU model, just then embedding a soiling model into a bigger context, and then translating percentage losses to soiling to energy losses. All of these problems we have solved internally, but we thought, why keep it to ourselves? Why not make it available to anybody? And this is really what we're doing today, and this is what I'm going to introduce. And then what this allows you to do is for organizations to implement, very easily build their own internal models and implement them across their entire lifetime. Organization, sorry. For performance and engineers to really go, or subject matter experts to go into the depth of modeling, building their own soiling models or adapting it to their site conditions, and not having to worry where the data comes from. And then, because I think this is most relevant to this audience, for researchers to use it for their research, and thereby just saving time on getting the data and having, let's say, a consistent approach. So just to make their research more efficient and then more straightforward. Now, let me show you how this looks like. And with that concludes my presentation. What I would like to do now is I will switch over to a live coding session. I hope that's not too technical. I hope there's a lot of Python developers or people with Python experience in the audience. If not, well, it will be a bit technical, but I hope I will make it easy to follow. What I want to look at is, just as an example, so Alvaro just showed us the HSU model and the Kimber model as well, showed us the HSU model and some nice graphs and parameter variations. And I just want to use these models and show you in how you would be able to do and perform this modeling yourself in just a few minutes. And as an example, I will use the Noor 4 solar power plant in Morocco, which I think is a nice example. So for this power plant, what I'm going to do is I will estimate soiling losses with the HSU model. I'm not saying the HSU model is the best model. There's a lot to improve. It's just a popular model, and it's very straightforward, right? So therefore, this is why I'm using it as an example. Then we want to understand the effect of rain cleaning threshold, the same as Alvaro explained in this concrete example. I will also then estimate energy losses, so going from a percentage loss to an energy loss. And I will show you what kind of an effect it has, this DC-AC ratio or clipping, which was also mentioned by both Leonardo and Alvaro. Right. And with that, let me switch over to a Jupyter notebook. I hope you can see this full screen. If not, please tell me. Okay, so here we have a Jupyter notebook, so which is my favorite way of using Python. And what I want to do now is I want to first get an estimate of what the soiling losses have been for this power plant in 2022. So what I'm doing is there's a few imports that I need to do. So the package that we're providing is called pvradar.sdk. And I need to import a few things from that I will go through one by one. The first thing I need to do is I need to specify a location and an interval. So this is the coordinates of the NUR4 power plant, and I just want to do all my simulations for the year 2022. So the goal is that I can just from pvlib.soiling import HSU. So this is my I just want to import the HSU model, and then what I want to do is I want to do soiling HSU equals HSU, so I call the HSU model, and then I pass rainfall. I need rainfall. I need a cleaning threshold. Well, let's use 1 for now. I need the tilt angle. Let's use 0, assuming this is the average tilt angle of my trackers, PM 2.5 and PM 10, right? So now what I want to do is I would just want to call this function, but actually I can't because I'm missing the rainfall, the PM 2.5 and PM 10 data. So this is where pvradar comes into play, or our package comes into play. It makes access to this data just so easy. So what you can do is you first create a site. So let's call our site NUR4. And you create a pvradar site. And what you need to pass is the location and the interval. So you're basically saying, well, I need data for this location and this interval, and let's call it NUR4. Right, you run this, and then what you can do, let's say we want rainfall. You say rainfall equals NUR4 dot, and then everything internally we call a resource. So now you want a resource which is called which is rainfall. So you need to basically with that resource command, you can get any data that you might need for your modeling for this location, and it's really a very big, very large number of different things that you can call. Let's start with rainfall. We go capital R dot. And you already see a list of available data that you can just call in a single line of code. We have air density, air temperature, angle of incidence, so many different things that you might need for soiling modeling or any other modeling, actually. What we want is rainfall. So we do rainfall, and I would like this to be to frequency, I want to have daily values, and I also want I want this in millimeters, and I can specify which data source this data should be taken from. And currently we have 4. So in this case, I would like to use MERA2. I run, and then the data has already been downloaded. Just to show you how it looks, what this data is, we can do a resource plot, which is a function from our package, and just pass rainfall. And this is how it looks like. Right? You immediately get the data. Now, this of course, this was the first. So now we have rainfall. What we're missing is PM 2.5 and PM 10. So let's quickly get that. PM 2.5 is equals NUR4 dot resource R dot PM. Now you can see that 2 PM 2.5 and PM 10. So we take the PM 2.5. We say 2 frequency. I again want daily values. I want this in grams per meter cube. And yeah, that's it. Just because there's only one data source in this case. So this is data from MERA2. And then I can just copy paste and do the same for the PM10 data. And I need to change it here. So I get the PM2.5 and the PM10 data, daily average concentrations in gram per cubic meter. I run this, and then I'm ready to run my HSU model. Because the HSU model produces a soiling ratio, and I want a soiling level, I will do 1 minus. I run. All right, so HSU model done. And now I can just do another resource plot just to show the results. So let's do soiling HSU, soiling HSU, and rainfall. So this is the typical plot, the same that Alvaro has been showing. So usually soiling level and rainfall. I run, and then here's my result. So I see my rainfall. You see that here, for example, it rained a lot, 66 millimeters, a strong rain, which coincides with the HSU model predicting that there's no soiling. And then during the dry season, my soiling goes up until reaching 4% apparently, and so forth, right? So this was very easy. And yeah, this was very easy. I'm not saying that this is the perfect model. I'm just saying if you wanted to use this model, this is how easy it would be using the package. Now, Alvaro, in his presentation, he showed us that certain parameters of this model have a very big effect. For example, the cleaning threshold. So just to show you, let's try to understand what kind of an effect this cleaning threshold has. What I will do is I will say, okay, soiling HSU, let's recall this soiling HSU 1 because I'm using a cleaning threshold of 1 millimeter. And let's create 2 copies of this. And then we say this is 2 and this is 3. So we use cleaning threshold of 2 millimeters and of 3 millimeters, but using the same rainfall and the same particulate matter. We run this, and then I just need to copy that into my resource plot. And right away, I get now the results of this soiling model using 3 different cleaning thresholds. Currently, the labels are off, right? But you basically, this is something that could be easily fixed, but to win some time, I'm not going to do it. But so the blue line is the same that we had before. So this is what you would get, assuming that 1 millimeter of rain would be enough to clean. This one is assuming 2 millimeters, and this one is assuming 3 millimeters. And of course, now what I could do, as Alvaro suggested, is I can also create a different function that introduces the idea of a partial cleaning. And yeah, but always I will need the data, and this is then how you could run the calculation. Okay, so this is the first example I want to do. So you can just run different soiling models and see the effect. If I wanted to have a different location, the only thing I need to do is change the location up here. If I want to have a different year, I need to change the year. The data will always be downloaded automatically for any location. Now, this is the first thing I wanted to show you. And the second thing I want to show you is what kind of impact this soiling could have on energy production of this power plant. So for that, I need to add a technical design to my site. So currently my site just knows where it is, but it doesn't know anything about the power plant build. So what I will do is I will say nur4.design is equal, and then we make a tracker design because this is a tracked power plant. And you can see that, so this introduces a simplified design. So it's not the most complex and you can go, but it's an easy way of introducing a simplified design to your site. You can see that there's many different, so you can define the access heights, many different parameters. There are defaults for all of them. The only thing that I want to change from the defaults is the DC capacity. So I would just say DC capacity is, and I looked it up, nur4 apparently is 72 megawatt, although I think this is the AC capacity, but let's assume it's the DC capacity. So we do 72 megawatt peak, and then we need to, because the definition is in watt, we need to multiply with 1e6, so 1 million. So to go from watts to megawatts. And then I will introduce a DC-AC ratio of 1.0. Let's start with 1.0. So this creates the design. And then with the design created, what I can do is I have access to more resources that require this design. Specifically, let's say I want the DC power, and I go nur4.resource. It's always nur4.resource. I do r dot, and then I type power, and I have, as you can see, there's 4 different options. So I can have the AC power, the DC power, grid power, and inverter power. So this is the power at different parts of the energy model then thereby including or not including certain losses. So DC loss, I want the DC power. I would say I want this hourly, so this is default units, so I won't change this. What I want to change is the unit. Usually it comes back in watts. I want megawatts. Let's do the same for the AC power. Right. So then we just change the AC here. And this calculates DC and AC power for my power plant. And then I can just go again, do my resource plot and do DC power and AC power. And I plot this. So this shows me my DC and AC power for a 72 megawatt power plant at the location of NUR 4. What you can see here, if you zoom in a little bit in, is that in summer, we have this effect that Leonardo pointed out. We have some clipping over the highest irradiance hours of the day. And this, of course, will lead to some reduction of my soiling losses, right? Because when the inverter already works at 100% capacity, it doesn't really matter if there is a little bit of dust on it. Just to show you the effect, this clipping has been introduced a few times. We can just change the DC-AC ratio. Let's change it to 1.2. We re-execute this part, and we now get what would happen if we had a 1.2 DC-AC ratio. And then, of course, clipping is much more pronounced effect in this power plant. All right. Okay, now we have a notion of the power production. Let's switch over to energy production. So the last thing I want to do to conclude this little demo is I want to do a resource plot. Resource plot showing the energy, let's say the grid energy without soiling and the grid energy with soiling. Right? So again, I need to calculate these two. So let's start with the easier one, and that is the without soiling. Because this one is just a simple resource call. I can just go grid energy without soiling means NUR4 dot resource R dot grid energy. And then we just define the unit. I would like to have this in megawatt hours, and I would like to have daily totals. So I will define the frequency to be daily. And this already gives me my first part, my daily total energy output without soiling. Now I want to have the same, but with soiling. So for that, well, this is maybe a little bit more advanced, but yeah, there's a very easy way of basically introducing soiling to the yield estimation in the back. And what you need to do is NUR4.hooks. I say for resource, so for my soiling loss factor. So in the back, there's a yield estimation model running, which at some point uses a soiling loss factor in the yield estimation model. And whenever that happens, currently it uses no losses. I would like to use something else. I would like to use my soiling HSU 3 millimeters. So I'm basically saying whenever you need soiling in the grid in the yield modeling, please use this soiling that I generated before. And then with that, I can just recall this. And now it is with soiling. And now I don't understand why this is. One second. Oh, yeah, I'm missing the word with. All right. We run this and we run this. So what this gives you, and let's just throw in there the soiling HSU3. So here on top, we now have the total daily, so it says here, total daily grid energy of NUR4 in megawatt hours with and without soiling. So as we can see here, yeah, there is a big difference at this point in time. But right here, the difference isn't too big, although we have 6-7% of soiling losses. Why is that? Because of the clipping. So if we want to see how big the effect would be with a different DC-AC ratio, we can just go up here, change the DC-AC ratio back to 1.0 and execute everything. It creates a new production profile. And it will also show you how much more severe the soiling losses will be. as last thing, let's maybe calculate this. So let's say total energy without soiling is equal. So we take the grid energy without soiling, dot sum. So that's the total production without, and then we can do total production with soiling. Right, we run this, and then we can calculate our soiling loss fraction by just saying the total energy without soiling minus the total energy with soiling divided by the total energy without soiling times 100 to get it in percent. So in 2022, assuming this soiling, my average energy loss would have been 3.18% of the total production. And then if I go up here, I change this back to 1.3, right? With a higher DC-AC ratio, I can see that this value, because of the clipping, goes down to just 1.35%. Right. And I think with this, I can conclude my demo. I hope this wasn't going too much into depth. And I hope I was able to show that with this library, it is very easy and very straightforward to do this type of analysis. And with that, I will go back to my presentation.
Thank you so much, Tore.
Am I out of time already?
No,
I have 2 more slides. Okay, sorry. Well, back to my presentation. I just want to let some final words. If you like this tool, if you would like to use it yourself, well, we have 2 more webinars coming up where we go more into depth, which you are very much invited to participate in. And this is for Python program or for researchers or for people that are regularly modeling in Python. So it's a little bit advanced Python required. Yeah, in the 2 more, we have 2 more webinars coming up, and you're very much invited to join. And also, you're very much invited to start using the Python package and do exactly what I've just been doing if you want today. It is possible for you can just install the package on your machine using the typical pip install pvradar -sdk. What you do need is an API key to access all the data. This key is free to get. You just need to request it from our website. So that's the last thing I'm going to show. If you go on pvradar.com, this is what you will see. This is our website. And then here in the middle, there is the documentation section. If you click on that, you will be transferred to a different page. And right here on the left, you have the installation instructions. Well, you have a lot of information and documentation, of course, but you also have the documentation instructions. So here it tells you exactly how to install and how to get your API key. Right, and with that, I think I will go back to the presentation and I'm ready for questions.
Okay. Thank you, Tore. Sorry for interrupting you earlier. Let's see if there are any raised hands. I see one. Bienvenu, Sumaili.
Yes.
Go ahead, please.
Thank you, sir, for this presentation and presenting the pvradar package. My question is, does this package take into account the dust disposition after rain or before rain? Because sometimes when I notice, because I'm from a tropical country, is that wet surfaces can increase adhesion dramatically. And also, a small amount of rain can mobilize the dust into mud-like patches. So does the pvradar take that into account to model soiling, or may this be maybe some enhancement perspectives?
Mm-hmm. Oh, thank you very much for your question. I think, yeah, sometimes something maybe I forgot to mention, or something I need to point out a little more. So what I just so we as PV Radar, we offer two things basically. So we have developed our own internal soiling model, and the answer to your question whether we do take this into account, yes, we try to. I mean, it's always difficult to take into account every possible effect, but we try to take into account these kind of effects in our internal PV Radar model. What I was introducing today is a toolbox that allows you to create your own modeling. So what I hope I was able to show is that if you wanted to create a model and let's say you have a site where you see this kind of behavior, the PV SDK, so the Python package, allows you to very easily build a model yourself that takes into consideration any effect that you would like to take into consideration, and then model the impact on energy production. I hope this was well. I understand that in order to do that, you have to look a little bit more into it. But also, it was a very warm invitation. If you want to reach out, we can also look into this particular problem in a call. I can help you do exactly what you asked to do.
Thank you very much.
Thank you. Let's see if there is any other question coming up. So I will probably, meanwhile, Tore, ask you the same question was done earlier to Alvaro. What is the main challenge, from your experience, also again from your field experience in modeling soiling?
What is the biggest challenge?
Yeah, in simulating the real soiling that occurs on PV systems.
Yeah, I think that the biggest challenge is related to, I mean, let's say most validation data that is available is for areas where there is a lot of, we have a lot of dust soiling, right? So we have measurements in southern Spain and Morocco and California, where it's typically regions where there's a lot of dust soiling. So if you have measured just a few months, you will already see something losses up to 10%. So there's an interesting and steep growth over a short amount of time. And then usually it's sites that do see cleaning. So even if there was, and then the assumption, so for these sites, the assumption of a complete cleaning by rain are not that bad, I would say. Not 100% maybe, but close. So it's reasonably, so the HSE model, for example, does a reasonably good job. But then we have sites like in Germany, for example, where if you apply the same model, you get to losses close to zero just because it rains so often. Yet there are places that have that see a growth of soiling over multiple years, and this is a phenomenon that is not yet very well understood, I would say, and this is mostly because there are so few measurements available which show the behavior or the growth of soiling over multiple years, which are unaffected by anything else, where you can really see, okay, this is just soiling, and it's just because of the growth of that thing. So that I would say, so this sticky soiling or pollen soiling, this is the main challenge currently.
Thank you so much. Thanks again. If you have questions, you can keep writing them in the Q&A. We will take on them in the final panel. So thanks, Tore, for your presentation, and I leave the floor to Ale for the rest of the presentations.
Okay, thank you, Leo. So hello again, everybody. So our next speaker, I am pleased to introduce Fabian. He is a product owner for photovoltaics at Volatec. Also, he studied physics at the University of Munich and earned his PhD at the German Aerospace Center in Almeria, focusing on soiling on concentrated solar power plants. Dr. Fabian then spent 5 years leading international research projects on photovoltaics, resource assessments, performance modeling, and soiling at the German Aerospace Centers. In 2020, he joined Volatech, where he leads the development of PV drones inspection technology. So his talk today is about combining quantitative soiling detection and thermography for improved solar field performance optimizations. So Fabien, you have the floor.
Thank you very much, Ale, and thanks also for the previous talks that introduced this topic. You should be able to see my screen. Is that correct? No?
Not yet.
Yeah. Yeah. Sorry. So I have to select this screen, and now that should be coming up right now.
Good.
Right?
Good.
Okay. So yeah, thanks for the introduction. So I'll talk about our novel technology to detect soiling from drone images, and in general, what drones are used for in solar fields, just so you get an idea of what's happening there. So to present Volatech, we're a spin-off of the German Aerospace Center, DLR, so our former colleagues of yours, basically. We started off in concentrated. We developed like monitoring inspection solutions for drones. We are there like a market leader for those type of inspections in the CSP technology, and I then in my role took our existing tools over to today. So what can we do with drones? Yeah, so this is like we're providing the software, not the drones themselves, and we do not fly ourselves. That's what our customers do themselves. And then we create a digital twin before the process. We provide flight routes, and the customers take their drones to the field and fly according to the flight routes that we create. After the flight is finished, they upload the data to our portal, to our cloud, where it's analyzed. I'll go into detail on how that's been done in this presentation. And how results are reported later. And just a quick excursion is like pretty easy. A drone is not an expensive. You can go to any solar field and use that drone, apply that, and with our software, yeah, it's very easy to do that. In large solar fields, of course, the art is to detect or to geolocate, so to speak, the individual modules. So flying with your own drone gives you a lot of flexibility and autonomy to the customers, but I won't go into commercial details here because we're interested in science, no? So the first or main application of drones in solar fields, and that's a standard application, that's nothing new, is thermography. So you can see thermal images where we detect different types of faults. The standard procedure, you have different fault types where they're classified automatically by our software, and then also you can find them and you can walk around your solar field just like in Google Maps. You can find every module where you expect anomalies in your modules. So they include like hotspots, open circuit modules that are not connected, not contributing. There's bypass diodes, like in this case, that are activated. And what we deliver is like temperature details here for each single module, and also we estimate the performance loss. So we can quantify in the end how much loss you would expect for a certain module, and then also for the entire solar field. So that's thermography. That's something which is the base product, so to say, for in our PV spectrum. So some examples here. That's how a hotspot looks like. So warmer spot with more than 4 or 5 degrees of temperature difference, some cell is broken. Like, the reasons can be very, very different. Recently, we had a case where they used the solar field as a shooting range for guns. That's really weird. And we saw hotspots there, and they were always at the same spot of those modules. So it can be anything. That's what I'm trying to say with that example. But many times this analysis and these results are used to decide which panels you want to exchange and to improve the performance of your power plant, basically. Another example here. So basically, what happens with thermography is, if your solar module is not working 100% fine, what happens to the solar irradiance that hits the solar module? It's not converted to electricity so much as in a perfectly working module. No? And you can see this here. There's shading here. Those modules that are connected in the same string do not work perfectly, so they are warmer than modules adjacent to that, because here not 100%, not 20% or something like the efficiency of the solar module is converted to electricity, but less. And what's less is converted to temperature, so to heat. And that's what can be seen in the infrared that has not been connected here, or where there's a failure of bypass diode or something. So they show up as warmer than the rest. So anything that's not working well in the solar field shows as warm. RGB. So if we have a hotspot, we want to see if there's something going on. And of course, in that case here, a bird left its traces here. And if that happens, then these cells are affected because they are not contributing to the electricity production anymore. And that's what causes this hotspot in this case. Something showed as cooler than the rest, which is very unusual. So it's not a failure type. And looking at the RGB images, we found this guy here who is actually cleaning the solar field at this place. So the water just evaporates and cools down the solar modules. And there, of course, we can say that this is not an issue. It'll be at thermal equilibrium quickly after that. So that's thermography. And the reason or the logics behind our analysis are shown here. So for thermography and also for the RGB images, it's the same workflow. So these are examples of infrared images at the moment, but later we'll go into soiling where we use RGB. So just keep in mind, it's the same principle, working principle for both cameras. On the left, you can see the original drone images. So each photo here of a part of the solar field, and then the subsequent photo. Just, the drone flies along and it takes photos on the way. And there's 2 modules that I just selected randomly here as an example. But those 2 modules in that row are seen, of course, in this image, and then the next image as well, because the drone takes many images on its way over the solar field. And then we isolate each individual module that you see on each image over all the images where that module appears. So we get a stack of photos of photo sections for each module. So here we have just 2 depicted here, but in reality it's like 10 roughly for each module. We have that raw image then, or ortho image we call it. And we run on these stacks of images, we run our thermographic failure analysis, or also later the soiling analysis, which I'll come to in a minute. And there's certain characteristics. Bypass diode, for example, shows as this pattern, like 1/3 of the module is brighter. And then we run that on those 10 images. And if there's a big agreement between all 10, then we tell our algorithm that there's a bypass diode error in this case. And this can be shown later in our web app. So that's basically how we do thermography and where our soiling application was born from, basically. So that gives us the databases to analyze for soiling. Yeah, that's my next slide here. So soiling detection, just an overview to start with. This was developed together with the German Aerospace Center. I also formerly worked there and also started to work in image analysis here for quantification of soiling. So what we can do is we can detect the optical loss for due to soiling for entire solar fields. So there you can see a section of a solar field here on the map with the soiling loss scale. Here you can see an example where we cleaned 2 stripes of solar modules just to have a contrast in one measurement, and that's clear. I mean, clear meaning that those modules are nearly perfectly clean. And on the others, you can see that the typical pattern, that soiling was washed down to the lower parts of the modules. In the next steps, we convert this optical loss into electric performance loss, and to account for mismatch effects, because if you have inhomogeneous soiling, then the impact of soiling on the productivity or the production, pure optical losses you get from the soiling. And of course, the measurement can be done at the same flight with thermography, so there's no more effort required from the user, with some very specific examples at the end of this presentation. So I won't go into, just to give you the idea on how soiling actually appears and what's the difference here. You can see a contrast between those 3 clean modules and the ones that are slightly soiled next to them. And depending on from where you look at those modules, this difference appears to be stronger or less strong. No, so there seems to be some kind of dependence on the angle of view, where you put yourself to look onto those modules. They appear brighter or less bright. So if we're talking about this soiled area, but also if we're talking about the clean area, so the brightness changes, or soiling changes the brightness of modules. And that's actually the measurement principle that we use for this technology. So they appear brighter, but why is that? I mean, I just stole that graph from you, Alvaro. I hope you're not upset here, but just to make people remember that there's solar irradiance coming onto the module, and if you have dust particles, they do scattering. They scatter the light, So, and a solar module in the clean state appears dark. So the more soiling you have, more scattering you would also expect towards the drone camera, right? So that's the basic principle of what we're using in this technology. Of course, we have to look at it from different viewing angles, but we have a lot of information in the background. Like here, we have a stack of 10 images, and for each of those images, we know perfectly where the drone was. We know how the module was oriented. So we have this information from the drones. We know which time of the day it is. So, and the dust type is a different topic. You have to do some type of calibration for that because different dust types sticks, and that has to be accounted for. Yeah, but that's a basic principle. So the brighter a solar module is, the dirtier it also is, in certain limits, of course. So that's then here you have the sun as a light source. Just here, then you get a certain amount of radiance and sun camera. And the camera camera is basically used next to this also. That's not straightforward because your mobile camera or something, that's a similar camera that's built in here. They do camera or brightness corrections that are not all that straightforward, but we do some tricks to compensate for that. And so we get separate or different contributions. So the reflected background, so to say, like the footprint of the module itself, we can see is one contribution to the camera signal. Also the background that is reflected. So if the camera looks down to here, then it also sees a part of that sky portion that is reflected over the glass into the camera, scattering that I just mentioned. And we have to separate these contributions to isolate the scattered portion of the light here. And that's why we need at least one clean module in the solar field, because that gives us the zero line. Without any soiling, you would get just those two contributions, and everything that's added is attributed to dust particles. So that's basically the measurement principle. So the RGB, or RGB is the brightness, like of the visual camera, is composed by, like in this case, is dependent on the irradiance, and here you get also the scattered irradiance for dirty. Or there's a scientific publication out that goes into a lot of details here, which I cannot go into depth in this presentation, but basically what it describes is a test measurement on 4 modules that are all, each of these is measured individually for with high quality for reference soiling ratio. Module 1 is clean, so that's a reference, and module 2 is used for a calibration, so to know the dust type, because here you know the soiling level, and then that calibration is applied to modules 3 and 4, and then this is rotated, so 2, 3, and 4, then calibration is taken from 3, and those two are analyzed and so forth. That delivers this type of results. So the reference here is shown in the lower number, and the detected soiling ratio from the drone images is shown in the upper number, and you see quite a good agreement on that. So that's for single modules, scientific paper, and for several campaigns, it shows quite a good correlation here. But of course, we as Volatech want to work with big solar fields. So 4 modules is not nearly sufficient to to detect soiling in big solar fields. So what we had to do is scale up this technology. From the scientific principle, we're going to big fields, and the art here is to get everything running as smoothly as possible and making it work. For without with a compromise between accuracy and practicability. So we did that in the spring of 24. We did a upscaling campaign on a 10 megawatt solar field in Spain. Some images can be seen here. Me looking at those modules around, and there's the drone down there. So here, that was our handwritten plan with a lot of marks and everything. So we cleaned a lot of modules. So in this solar field, this is just one section. It's just a very small section of this solar field. And then we had, in red, we had, because in the solar field, you would not just measure on one module. The smallest unit you can measure is actually a string of, in this case, was 16 modules, I think. So we took those, we took reference measurements there by opening the box and doing some weird stuff with electric with an electrician, a professional one, and we could determine the true soiling loss of that string by measuring before and after cleaning, measuring the production before and after cleaning. Of course, this is highly accurate measurements here on single modules, but for string measurements, you get well, the uncertainty is not so clear, but it's around 3%, what we estimated in terms of soiling loss points, 3%. Anyways, if we take those 4 strings from that measurement campaign and compared the reference measurement to what our algorithm said and estimated, we just have to take that entire string. So that's one of those strings. We can see this, and here we can see the reference value that we determined with the electrical measurement for that string. So it's not a single module. And the agreement here was pretty good. So you can see some deviations here, probably, it's like a 3%. So it's in the range of the reference measurement accuracy. So that's where we're getting at. And you see that for those 4 electric measurements, they took us more time actually than flying the drone over the entire solar field. And we only get like a value for 4 times 16 modules, whereas from the drone, we get a value for every single module in the solar field down to the cell level. So you can see here, there's single cells. For each single cell, we specify how much it's going to lose in terms of soiling, optical losses. If we plot that on a graph, you can see the electrical reference measurement here on the X, and on Y, you can see how we estimate the soiling for these strings. The uncertainty of the reference measurement is this, at least touch that gray area, and that's our estimate for accuracy. That's statistical because we have to take 16 modules and not just one, so we get a bigger spread here. Deviations are less, like in average, they're less than 3%, but of course this has to be taken with caution because of the uncertainty in the reference measurement. But the agreement is there. There's a clear tendency. If we say there's higher soiling, then most probably also the reference will show that. So that's nice, no? That's how we do that. But what is it actually good for? I mean, soiling, we talked a lot about modeling. So you want to optimize the time of cleaning and also know something more about the nature of soiling. And yeah, but what can we apply these maps in that regard? So our vision is to take some data from feed-in tariffs and also weather forecasts to enhance a little bit the depth of our data. And knowing the solar field entirely, like the distribution of soiling over the solar field, we can do something like recommend that only 52% in that case, in that example, should be cleaned at a certain point in time. It's like more profitable because if you have inhomogeneous soiling, of course, then you can save on cleaning. For example, a customer in Spain, he cleaned like just 50% of the solar field each year, and then doing a soiling scan with us before the cleaning, they could recover like 80% of the soiling losses by just cleaning 50% of the field. So just imagine that, no? And a cleaning can be quite expensive. Working on that, improving on that, because it's different and many do now. Just show you some cases from actual measurements that we did with customers to show you what is possible with that new dimension of soiling quantification. Because dimension of time, There's sensors, there's models that can tell you one line of soiling loss over time, how that's going up and down, and do another thing. But the new dimension is now the spatial distribution. So here you can see one case in Morocco, actually, in a 70 megawatt plant. Heavy soiling, it's in the very south of Morocco, so 0.8 per day. That's heavy soiling conditions in a sand. Detecting soiling over that solar field, they detected that their cleaning service was very unreliable. So here you can see that many rows are cleaned pretty well, but then they just jumped a few rows where they just did not bother to clean. And in a 70 megawatt peak field, that's quite significant. It's not so easy to find those spots. No, if your external cleaning service provider comes to the field, signing a contract saying, I will clean all your field up to like 95% of cleanliness. So that's typical contracts. No, they pay a lot of money for that. 25,000 in that case. That's against contract. And it's hard to prove actually that something has been lost. So or jumped in that case. Here, average losses were 15-20%. And we report this here module by module. You can get the losses, and of course they showed they had to fix that, and they actually got a free cleaning for that. And knowing, like, if that service provider knows about that technology, then they will take good care at this plant to clean very, very well the next time. If cleaning is not done perfectly, you can lose a lot of money still. So that's basically the message, what can come out of this. That's another example of incomplete cleanings. So some brushes, they ran out of water or something. They were not bothered to finish that cleaning that line here. And that was not only in this single line, but in several places, like 10%, 8 to 10% here. And they could also do the same thing, like tell their cleaning provider to come back and fix that. And of course, in the future, they will clean better. That's for sure. Oh no, that was Turkey. Right. That was Turkey. 50 megawatt. So that's quite significant savings you can get there. Also, probably also interesting for your see, like weather effects here on the edges of that solar field, on the edges, no? That's on the heaviest soiling affected modules here, you get 18% of losses, and knowing that they affect the entire string of modules that is connected behind, the area to clean is quite small. And in a 50 megawatt field, that was also Turkey, if you have somebody there all the time, then you just send them out to clean those few modules, the rest, and you can actually increase your earnings significantly, knowing that. Of course, somebody might say, well, I can see that if I go to some edges or something's heavier soiled than other regions, that's not the case. I'll show you in a minute in our web application. Is that thermography should be done in clean conditions. Like many people do it right after cleaning, or they send cleaning taking a thermography scan. A site here was heavily soiling effect 50 megawatt field. It takes like 2 weeks to clean, but in a sand desert, in 2 weeks the first module you cleaned will be dirty again after 2 weeks. So you have that problem of never actually having the solar field in a condition. And so here, knowing the soiling, and if it's like really concentrated at some point, so that's a very heavy soiling example. You can see the RGB image here, and that's our map, what we derived from there. And you can see those hotspots of soiling, and they convert to thermal hotspots because, as I said before, like in this example here, if you cover what up, because it won't contribute to the electricity production so much anymore. And that's exactly what happens here. So if you have single cells that are really heavily soiled or more strongly soiled than others, you will see that in the thermal image of the camera. So you can see hotspots here. And knowing both, we can say that's, you just have to clean the modules. No? Having both in the same place can improve the knowledge here. Yeah, we're running out of time, but there's one more thing, probably not so in, that's the future. So there's drone for drone inspections. So that's something we also work with, and that can also, because scanning frequency can be increased significantly. So that's just this idea that the drone here from the docking station can take a soiling scan basically every few days, depending on the size of the solar field. Yeah, so to conclude, drones are already used as a standard tools in PV operations, mainly for thermography, and also for some visual inspections. If something's wrong, then people can go there and don't have to walk there. They can fly there, basically. And we know soiling from drones. I just explained that it's based on light scattering at dust particles, solar fields. We looked into some application cases. Drone docking stations can increase the measurement frequency, and this is a pretty new technology. So we launched it at the start of this year. Academic background or surrounding, like if you have some test site or whatever over several modules, then feel free to come up to me. I'm happy to exchange ideas and yeah, for any type of collaboration. Great, that's my contact. We'll be at Intersolar. Feel free, and I'm happy to answer your questions if there are any.
Thank you, Fabian. Thank you, Fabian, for your presentation. So I think that you will have a lot of questions as you have, I think, a little bit bad connection. So I will go to the audience. If
Okay.
someone, yeah, maybe we can discuss further in the panel. So we have a question from the audience. I think so. Please, anyone?
I wanted to show you was,
yeah.
Sorry,
You can raise your hand if you have any questions. Okay, so I have a question, Fabian. So regarding the using drones for inspection, they are still competing with, if we need to say, electrical inspections. Fabian?
Sorry, I have a bad connection actually.
Yeah,
Could you
yeah,
repeat
I think
the
so.
question? Yes.
So I was talking about in your point of view, do you think that drone inspection can still compete with electrical inspection in the field, of course?
Yes, it's to like electrical inspection. Do you mean electricians that go to the field and
measure or
individual strings, or do you mean monitoring?
Monitoring, and also inspection. It can be hard, but monitoring.
Well, the monitoring data is a very, very fundamental tool in asset management or in managing your solar field. Of course, definitely, that's maybe the most important one because you get daily it's happening in your solar field, and if there's something going really wrong. But it has to be complemented with thermography, because if you know, then you'll causes that issue, and that's where drone inspections can help, because there you can detect from the thermal signal, you can see which modules are affected or faulty and which measures to take, like if you want to exchange that and how much loss you have and all that stuff. So they're not competitors, they are working together in the best case. Yeah.
Okay, thank you so much, Fabian. So I think we can move on to our next speaker, and we can further discuss the topics in the panel. So our next speaker is Professor Leonardo Michelli. I take the time to introduce him again, as he was already introduced by Professor Ahmed Inawi during his plenary session. But I need to talk with the audience of this workshop. So Professor Leonardo Michelli is an associate professor at the Department of Astronautical, Electrical and Energy Engineering at the Sapienza University of Rome. He holds a PhD in renewable energy from the University of Exeter in the UK, and has carried out research at prestigious institutions such as the INRAEL at the United States and the University of Jaén in Spain. His research mainly focuses on the modeling and optimization of photovoltaic systems, with a special emphasis on reducing losses due to soiling and techno-economic analysis of floating PV systems. Professor Michelli has received several distinguished awards and fellowships, including the Marie Slopes Curie Fellowship and the Rita Levi Montalcini Grant. He also actively contributes to the International Energy Agency PAS Task 13 on PV reliability and performances. So the talk of today of Professor Michelli is the challenges in soil mapping and mitigations. So Michelli, you have the floor.
Thank you, Ali.
Thank you.
So I'm gonna share my screen. First of all, again, thanks everyone for being here, still, being present. Thanks to the organizers for involving me with this workshop. And many, many thanks to all the previous speakers that really gave very good overview of all the, R&D, all the status and the evolution of how soiling is handled by our community. In this talk, I'm gonna add another piece to our discussion, and in particular, we're going to be focusing mainly on soil mitigation, starting with a brief overview of the current status, and then focusing a bit on some of the perspective that we expect for soil mitigation, how this is going to be changing in the near future, how we expect it to change. So first of all, when I mentioned soil mitigation, I really refer to any activity that is meant to either reduce the accumulation of soiling, remove soiling that has accumulated or limit anyway its effects on photovoltaic panels. So there have been already some of those have been mentioned, such as cleanings. There have been few questions about anti-soiling coatings. But what we have to keep in mind is that any soiling mitigation activity, any soiling mitigation solutions, in order to be profitable and therefore in order to be applied, has to generate revenues that are greater than their cost. Indeed, when we apply soiling mitigation, we have some expenses that we will have to pay. These are either capital costs needed to cover the initial materials, such as in the case of deposition of coatings, or for the acquisition of cleaning robots, or we have, for example, costs related to human labor or to resources that might be needed, such as electricity or water. On the other hand, we have additional revenues that we can get from mitigating the soiling losses, and these are due to the recovered energy, the amount of energy we would otherwise lose because of soiling that can be converted into revenues. So we can by applying an approximation, simple approximation, saying that the revenues, the additional revenues achievable through soiling mitigation are essentially the product of the recovered energy and the electricity price. Recovered energy in kilowatt hour, for example, and the electricity price in euros per kilowatt hour or dollars per kilowatt hour. By combining these two, we will know how much we can get from the recovered energy. So the soiling mitigation solutions that are available nowadays were actually initially presented by BESA, or let's say categorized by BESA a few years ago, and they are essentially divided in two broad categories. On one side, indeed, we have the preventive strategies. So those solutions that are aimed to limit the accumulation of soiling in first place. These are, for example, the previously mentioned anti-soiling coatings that will either favor the resuspension or rebound of particles, so avoiding that the particles actually stay on the surface of the modules, or facilitate the natural removal. However, within the preventive strategies, we should also mention, for example, site selection or site adaptation, because the site selection itself can be seen as a soiling mitigation strategy if the energy and economic effect of soiling are taken into account when a new PV system is designed and therefore its location is selected. However, as I also mentioned earlier, there is essentially no solution right now that makes it possible not to consider corrective strategies as a way to mitigate the effect of soiling. In this case, we are taking an action actually to remove soiling once it has already accumulated on the photovoltaic panels. Corrective strategies or cleanings can actually be performed by natural agents, therefore happens for free, but as was said earlier, they are probably not as effective as artificial cleanings, and clearly they cannot be controlled. So even if we get some benefits from rainfall, we cannot just rely on rainfalls for keeping our modules clean. So for these reasons, by far the most common soiling mitigation approach still nowadays is through the use of artificial cleanings, and in particular mechanical cleanings, where we either use robots or some semi-automatic system to clean down our photovoltaic array, or either we have O&M team sent out with brushes and squeegee to manually clean down the systems. So depending on the location, depending on the amount of time, but also depending on the economic conditions and the characteristics of the site, we can actually select which type of cleaning we prefer. And what we have seen typically is that locations where the cost of labor is low, we might prefer manual cleaning might be preferred, while in those locations where soiling is very intense and therefore frequent cleanings, maybe overnight, maybe every 2 nights cleanings are needed, a fully automatic approach is preferred, which anyway requires a high capital investment and has high upfront cost, but limits a lot the cost for human labors, because we have robots that will automatically activate and automatically clean a full array, a full string of modules almost without the need of any operator. What we see at our latitudes in most of Europe, in the United States, is actually a semi-automatic approach, where the cleaning devices are actually mounted onto trucks, or portable robots are employed, and therefore we have some kind of automation in the cleaning process, but we still require an operator to actually make the cleaning possible. So again, depending on the type of solution, on the characteristic of the system, we might decide which type of solution to adapt to mitigate our cleaning strategy. However, we have to take into account that in order to perform an accurate or to develop an accurate mitigation schedule, we really have to understand which is the level of our losses. Also, this was a topic that was touched earlier. What we need to do is actually understanding the losses we are experiencing, so that we can estimate the recovered energy, and by using information we have on the electricity price, therefore evaluate our revenues. So what is typically done nowadays is actually to take into account losses that are either measured at the site or estimated using models, combine them with electricity price, and then determine which is the most appropriate mitigation approach for our system. However, we also have to take into account that both the electricity grid and the way photovoltaic systems operate are changing. And what this means is that the monitored soiling losses might not be necessarily the soiling losses that the effective soiling losses that the system will experience. Okay, we have to start realizing that there might be a difference between the maximum power potentially produced by the module and the actual power that is transferred onto the AC side of a photovoltaic power system. So we have to take into account the new mechanisms are taking place, and these are, for example, the case of inverter saturation and curtailment. If you're not familiar with this, no worries, I will have a few slides on those. Tore earlier mentioned clipping as one of those in one of his examples. These are both mechanisms that again affect the amount of recoverable energy. So even if we measure soiling losses, we might actually not be able, because of inverter saturation and curtailment, to recover all the losses that we have because of soiling. And therefore, these two mechanisms might actually affect the maximum revenues that we might be able to achieve through soiling mitigation. So the first one is, as I said, inverter saturation. I might call it clipping. We are going to see what is it due to. So nowadays, when PV systems are deployed, they're actually designed to have an inverter that has a lower capacity compared to the DC side. The inverter is that element that is needed to convert the DC power, the DC energy produced by the module, into AC energy. However, what is happening? These are now intentionally undersized compared to the size, to the cumulative size of the photovoltaic modules, for cost optimization reasons, and in some cases also because of requirements from grid operators. So what is happening here? We know our modules are designed and they are tested under standard test conditions. However, they will very often not work close to their nominal capacity. So what is happening here? Since the inverter is an expensive component of the system, if I reduce its size, I will make it work closer to its maximum capacity for most of the time, and therefore I can actually maximize the investment and also maximize my my economic return. However, we have to take into account that when the system works closely or at its nominal power, we will have an excess energy produced by the DC side that cannot be converted into AC, that the inverter will not be able to convert into AC. So this is exactly what we call clipping on inverter saturation, is when actually the DC side works at a capacity that is higher than that is able to that the inverter is able to handle, and therefore we have a reduction in energy moving from DC into AC. So this is one of the cases. Typically, the inverter undersizing is quantified either through a ratio or through a parameter that is known as inverter loading ratio. The inverter loading ratio is actually is telling us the ratio between the DC side and the AC side. So in between the size of the modules and the size of the inverters. So on the left here, you actually have you know, the performance of a PV system on a clear day. And what is happening? So the system is performing, all the energy, or 95%, 99% of the energy is converted into AC, depending on the efficiency of the inverter. However, at some point, the systems, the modules start producing more energy than that the inverter is able to convert. So during the central hours of the day, actually the maximum energy is capped at this level, while we are losing all this area that is colored in red. So what is happening there? Even if we are cleaning the system and therefore, for example, recovering additional energy thanks to our cleaning effort, we are not seeing those benefits because that energy is anyway clipped, is anyway masked by clipping, by inverter saturation. So what is the size of this problem? Here on the right, you actually have some data showing you how the inverter loading ratio, again, the DC to AC ratio, has been increasing over time for utility scale systems in the US. You have different data for fixed and track systems, but we can just focus on the all PV data, so the average data for PV. And as you can see, from 2010 to 2022, the inverter loading ratio has actually been increasing from 20% or 1.2 up to 1.34, up to more than 1.3, with in some cases reaching values even higher than 1.4. So as you can see, right now we are already installing systems where the inverters is about 30% smaller compared to the maximum capacity of the DC systems. And as also mentioned in the myth-busting slide from Alvaro, we are often asked, again, as soiling researcher, whether clipping is enough to mask the soiling losses and therefore to get rid of the need for mitigating soiling. In order to answer that, we conducted a study with some colleagues from Sandia National Lab in the US, NREL from the US, as well as the University of Jaén. And we essentially investigated the extent of clipping over the US. So we started with some data downloaded from NREL NSRDB database at 5 minutes time interval. Then we used some typical temperature and power model to estimate the lossless energy yield of photovoltaic system. Then we used the previously mentioned Coelho and Boyle soiling model to estimate a soiling profile. And then we implemented a clipping model assuming an inverter loading ratio of 1.34. We calibrated and validated our data against the field measured data. And in particular, we validated our energy and clipping models against two sites made available through the NREL PV fleet. initiative. And here you see in red the actual data, actually plotted at hourly intervals, but we were using 5 minutes intervals. And in black, you see our model showing you how the energy was simulated and how clipping performed. And then you can also see how our model is also able to tell us which would have been the performance of the system if no clipping was taking place. Also, we recalibrated the Coelho and Boyle model using some actual data made available by Sandia in order to make sure to offer the most realistic soiling estimations. So we repeated the analysis, taking into account both a fixed system, installed at latitude, tilt, and south oriented, as well as horizontal single axis tracker systems. So the results are shown in this slide, where you have two columns. On the left, we have the results for fixed tilt system. On the right, we have a single axis tracker. Soiling losses are assumed to be the same for both types of the systems. And as you can see over the US, according to the Coelho and Boyle module, we have losses quite low in most of the land until we arrive in the Southwest, in Arizona, and in Southern California, where actually the losses start growing to values that can be as high as 8 to 9% per year. However, what happens when we apply clipping to those losses? Well, this is represented in this second line, where we see the absolute reduction in soiling loss, okay? How much these losses are reduced. And as you can see, these values is never greater than 1%, meaning that we are never gonna be able to reduce a 9% loss to less than 8%. As you can see, indeed, the absolute reduction again varies, is typically very close to 0.2 or lower than that, but in some cases it can raise. What does this mean? That actually, from a relative perspective, we can have reductions that are even close to 40% in soiling losses. However, these reductions shown here in the rather darker areas are happening in those regions where soiling losses are already low, okay, almost negligible. What is happening in those areas where soiling is most important is that actually the reduction in soiling is not so significant. We don't have such a significant masking of soiling due to clipping. Also, these images are showing to us that actually single axis tracker system, the clipping in single axis tracker systems seems to have a higher masking impact on soiling. So actually, if there is a mitigation effect from clipping on soiling, this is more intense in single axis horizontal track systems rather than on fixed tilt track systems. Why is this happening? This can be mainly attributed to the fact that actually there is a seasonal mismatch between the soiling ratio, so the fraction of energy passed by the that is the system produced despite soiling. Again, you can see the soiling ratio, as said earlier, as 1 minus the soiling loss, and the clipping time. So as you can see here in this graph, most of the losses occurring over the US are clearly occurring over summer, that are typically drier period where the soiling ratios can get quite low. Here you have data for 3 years, and as you can see, the minimum soiling ratios are typically registered in the summer period. However, clippings mainly occurred in spring and initial summertime, where soiling losses are not yet so high. Why is this happening? Because in those periods we have quite high radiation, we have, however, milder temperature, and thanks to the optimal tilt, the systems are producing quite a high amount of energy. However, in single axis trackers, what is happening? Clipping is mainly occurring in the summer period, because in this case, at noon and in the central hours of the day, the tilt angle is actually close to 0. And therefore, we need the summer to have a minimum angle of incidence, and therefore to have our peak energy production. So as you can see, in single axis tracker, we actually have clipping mainly occurring in summer, and this is why actually the mitigation effect on clipping is higher when we have a single axis tracker rather than a fixed tilt. However, we run this first analysis assuming a 1.34 loading ratio and assuming fixed performance losses on 10%. But we also wanted to test our model for heavier performance, in more clipping prone conditions. So what we did, we actually assume a higher inverter loading ratio of 1.45 and PV performance losses of 5%. What is happening then there? As you can see, actually in this case, assuming the same soiling losses, what we get is that the absolute reduction in soiling loss actually starts increasing up to 3% per year. And what does this mean is that actually now we are starting halving and reducing the soiling losses just because of clipping, even in those regions where the losses are more intense. So actually, in this case, under these conditions, we start seeing a substantial masking effect on soiling due to clipping. However, we have to take into account that even if this was true, it will hold true only in the initial year of the system. Because again, the gradation will take place after the system is commissioned. And again, these slides will mention, as mentioned before, will tell you how the clipped energy actually is reducing year after year because of degradation. So degradation consists, as you might know, in a gradual lose in efficiency of the system because the components age and because issues start appearing. So what is happening there? Actually, the peak power generated by the system starts lowering and lowering, and so clipping with time becomes less and less frequent. And that's why, for example, in this case, I believe in Colorado, we had a 5% energy that was clipped on the first year of commissioning of the system. This was then reduced to 3.6% by year 5, and by year 10, we had 2.3% of energy clipped only. So why is this important for soiling? Because what this means is that if clipping is becoming less frequent with time, soiling will become more and more visible, even if it was initially clipped. So even in those conditions where we might think that soiling is completely mitigated by inverter saturation, we will have to take into account that it might become more and more visible as the clipping effect vanish, as degradation grows. However, this is only the first case, the first mechanism that I mentioned. The second one is a mechanism that is becoming more and more common and is known as curtailment. So this is a mechanism that actually has been for several years already applied to wind energy, and it's becoming more and more common also for solar energy. So in this case, we have actually the grid imposing restriction on the maximum amount of energy that can be accepted. So what is happening? For example, during the central hours of the day, when we have an excess solar energy production, until a few years ago, we would assume that all that energy was accepted by the grid. Right now, because of the massive growth of photovoltaics and renewable in general, the grid starts saying that part of that energy cannot be accepted anymore. Now, here the situation changes a bit from country to country. In the case of Spain, if the curtailment, so if a restriction on the maximum amount of energy solar energy accepted by the grid is communicated 24 hours before the curtailment takes place, then this is not compensated. So energy that could be anyway produced by the system is not going to be sold to the grid and thus cannot be converted into a revenue. And these issues are increasing. Again, just reporting the case of Spain. On the left side, you can see how much of the daily PV energy has been curtailed since September 2022. Spain first started curtailing PV energy in April of that year. And as you can see, since then, about 2.4% of the energy that was produced in Spain was actually curtailed, with some significant peaks over some specific periods of the year. And according to some preliminary analysis we are conducting, what this shows is that clearly, if this energy cannot be sold to the grid, it will produce a loss in revenues and thus will reduce the profitability of the system, which is typically expressed by the net present value. And in particular, what we estimated is that the net present value of PV system might lower by 7.7% if the current curtailment rate will stay. However, again, we are talking about soiling. So why does this matter? Because if I cannot, so if I clean the system, but I do not see any gain in the energy that I can trade with the grid, I can sell to consumers, then I will not be incentivized to clean. And thus, also curtailments will have repercussions on the way we handle and mitigate soiling that we'll have to take into account more and more as the years go by. However, until now, I focused only on the first part of our equation. There is also a second term that we should be taking into account, because as you know, in most countries worldwide, electricity is sold in spot market. What does it mean is that the electricity price actually changes from day to day. Here is an example of how electricity price has been changing every day on average in Spain, in Italy, and in Portugal. And as you can see, the prices were fluctuating, but were always within 0 and 100 euros per megawatt until 2022. Then until 2020. Then in that year, we had the COVID lockdown that led to an incredible and unprecedented drop in the electricity price that was followed by the partly still ongoing energy crisis that has actually made the electricity price go up to, again, unprecedented level. So even the electricity price will change and will change significantly from day to day, from year to year, from season to season. And again, if the electricity price changes, also the incentives to clean a photovoltaic system will change. And this slide just shows you how, for example, the maximum allowed cleaning cost, so a proxy to say actually the revenues that one can make from cleaning a system in a southern location in Europe, has changed in between 2010 and 2019 just because of fluctuations in electricity prices. And clearly, you can expect that if the price continues to drop, the revenues made by cleaning could be even lower than the actual cost of cleaning. On the other way, if prices will go up, we can expect more and more cleanings to become profitable, and therefore to have owners and operators to be more and more incentivized to clean. However, we also have to take into account that the price, that the electricity price is not constant throughout the year, throughout the day, but actually even changes within the same day. This is represented here, where you can see for a European country how the electricity price has changed over the different hours of the day from 2020 to 2024. So each point in this graph is actually showing you which was the average price at which electricity was paid on that given year, normalized, so divided to the average price that was registered on that given year. So what is this point telling us, this graph telling us? If the line is above 1, it means that on that hour, we were actually getting a price that was higher than the yearly average. If the price is below 1, we are actually getting at that time a price that is typically lower than the average yearly price. And what do you see here? that since 2020, the average price in the central part of the days has been dropping, and have been dropping quite dramatically. Indeed, we see more and more electricity prices during the central hours of the day getting close to zero, or getting even to negative values. So we have to take into account that electricity price continuously change even from hour to hour, and that the time at which photovoltaic is producing energy is actually the time at which is going to be paid less. Electricity price is typically paid less. What does this mean? This actually opens to the possibility and make it possible also to partly contribute to the installation of battery energy systems, because this will allow actually to store part of the energy produced during the low price central hours of the day, and for example, sell it at times in which the electricity price is higher. As you can see here, for example, if we charge our battery, around 1, and then we sell them around 8, we can get an increase in price of about 60 euros per megawatt hour. So again, this stressed out the need for battery energy storages, because they can help not just saving the energy that would be otherwise curtailed by inverter saturation or curtailment, but could also help improving the revenues for owners and operators, thanks to selling the energy into time slots where the electricity prices are higher. So throughout this talk, I wanted to give you an overview of soiling mitigation strategies, which strategies exist, but I also wanted to highlight that cleanings are still the most common and widely used approach. However, I also want to warn that new mechanisms are taking place in our electricity grid, in our power plants. And therefore, we are having effects such as inverter saturation and green curtailment that can actually lead to masking part of the energy that could be otherwise recovered through soiling mitigation, reducing the revenues we can make through this action. Also, we have to take into account that the electricity price fluctuates and are actually lowering, reducing thus also the incentive to clean. In all this perspective, actually battery energy storage system can play a substantial role, because they can help storing part of the energy that would be otherwise lost to clipping, lost to curtailment, and could also help selling energy that is produced at time of low price, selling it to times of high electricity price, again improving the economic returns of soiling mitigation. So thanks to all of you for your attention.
Thank you, Leo, for your presentation. So it was amazing to wrap up all the last presentation, I think. So I give the floor to the audience if there is any questions. I think we have questions here in the Q&A, but 2 is addressed to Fabian, and maybe you have a question about from Carlos Rosa, I think from the last panel. Are the wind patterns being taken into account somehow in the soil losses prediction or estimations? Thank you for your interest. Okay.
Sorry, Ale, the
You didn't
connection
hear?
broke. No.
Okay. So we have a question from Carlos Rosa.
Okay.
So are the wind patterns being taken into account somehow in the soil losses prediction or estimations? So I think it is from the last panel. So we didn't answer it. Maybe we can answer it now.
Yeah, so I can give my answer. I think Alvaro also partly addressed this, and Fabian, I believe, has some work on it. As we have seen, actually is not yet taken into account the wind pattern. So the most common models nowadays do not consider the effect of wind, but clearly there is, more work should be done in that direction, because the wind plays a role in, the way particles deposit on the surface and get resuspended and rebounded. So hopefully, we will be able to model better in the future how wind patterns contribute to dust deposition and removal. And in addition to that, yes, hopefully we will also be able to better, work on how dust is distributed by wind across a photovoltaic power plant.
Okay, thank you. So we have a question from Bosha.
Yes, thank you, Ala. Thank you for you all for the interesting keynotes. So I have two questions to Leonardo regarding the clipping. So what is the period when the clipping can become less frequent and have less effect? Like what is the period in the lifetime of an installation?
When it becomes more frequent. So, correct?
Yes.
So yeah, now what we have seen is actually that clippings becomes more frequent in, wait, I can go back to the slide, but at least for fixed tilt systems, it seems to become more frequent in the springtime, if they are optimally oriented. Because again, there are, at least for the US, we found very good conditions in terms of temperature and irradiance. While,
no, I mean,
yeah,
yes.
go ahead. Go ahead.
Yeah, I know. I'm talking about the lifetime of like an installation. You said like after some after some years, this effect will be less significant. So like what is the period? For example, 3 years, 4 years, or 5 years, we have a severe effect of this clipping, but after that it is less significant. I'm asking about this number of years.
Okay, I see what you mean. So what we found in our analysis, but again, it will depend on the assumptions and the type of system you have. So we had a 10% fixed loss in our analysis. We have a 1.34 inverter loading ratio. And what we found was that depending on the location where you are, and depending also on how much soiling you have, the clipping will completely disappear in between, in between 20 to 30 years. So will still take time for clipping to completely disappear. But again, soiling will become more and more visible gradually. Unless, clearly, inverter is replaced. At that point, essentially you might decide to, I don't know, undersize again your inverter based on the degradation of your system and so on. So it really is a site-specific question. What I wanted to highlight is that really you have to take into account that degradation will make your soiling more and more visible.
Okay, I see. So considering this, do you think the cleaning frequency suggested for a specific site should consider the clipping period, as during this period, cleaning expenses will be, I think, a loss?
Yes, that's what, my message, you have to consider clipping. So, you might install a soiling station, you might monitor soiling losses, but you will have to take into account that even if you clean your system, you will not be able, if clipping is there, to convert or to get back to the full efficiency of your module, the full energy yield. So our analysis shows that even with clipping, at least in typical configurations, you should still care about soiling. But again, you should take into account that actually the revenues you expect, the energy yield you expect might be lower, again, because of inverter saturation.
Okay, thank you for your answers. Thank you.
Thank you.
So thank you, Bushra, for your questions. So what do you think, Leo? We move on to the panel with all the speakers?
Yeah, we can move on.
Yeah, because we have many questions for the other keynotes.
Mm-hmm.
So
yeah. So let me stop sharing my presentation.
So if can Fabian and Alvaro show us, I think that Thor excused to be in this panel. So
yeah, we'll go back to a question that was raised for Alvaro. What is the significance of the central hours around noon while you were considering irradiance above 700 watt per meter square?
Yeah, I think using those hours allows us to avoid angular effects. So we have lower incidence angles, so the angular losses are also lower. So we can easily differentiate between soiling losses and angular losses. So considering only central hours, we can better quantify the impact of soiling.
Okay. Thank you.
I think we have another question to Alvaro. What is the significance of the central hour around noon and POA? I think this one is all. I think it was already answered. How are the soiling intervals? Yeah, how are the soiling intervals determined, and what role does the slope of each interval play in the calculation of soiling rates?
Okay, so yeah, basically those methods identify the intervals by looking at the change points in the performance profile of PV systems. So in the case of cleanings, if they detect a sharp increase in the performance ratio, you can easily identify that that's a cleaning event. So that's the end of a soiling accumulation period. That's why people typically identified or divided the data set into periods, and the significance of the soil of the slope, basically the slope of each deposition period is the soiling rate. So it's used to calculate the soiling losses.
Okay, thank you. And another question about Monte Carlo simulation model. How is running, or?
I think maybe Leo can provide a better response to that question. There are some libraries, some packages in Python that allow you to easily conduct these Monte Carlo simulations. I think, Leo, you have way more experience than me on that topic.
Yeah, so the idea behind that Monte Carlo approach was essentially to assess the robustness of the data that were given in input. So actually there is both Monte Carlo and bootstrapping taking place at the same time. So the Monte Carlo means that the same process is iterated multiple times, and the random variable there is that some data are taken out from the analysis each time. So if you have a very clear soiling trend, essentially each iteration, independently of the points that you take out, will give you a very similar results. However, if your data are very noisy, every time you take out some data points from the trend, you will see actually a different slope and inclination. And so that's how the Monte Carlo essentially happens. So you repeat the analysis, the method applies it 1000 times. At each iteration, some data points are randomly removed from the data to see if the soiling extraction is consistent or if it changes.
Okay, thank you, Leo. I think we still have some couple of questions for Fabian, I think. Thank you. What threshold or indicator are used in order to decide if a hotspot is due to soiling or a hardware defect? Yeah.
Yeah, I already answered that question in written text. So what we do is, our knowledge is that we know what losses are caused by soiling, like which optical losses are caused by soiling. And we actually use pvlib, which is an open library, Python, where you can add, or where you can enter like irradiance values for each single cell. So that's what we do. And then pvlib tells us in which cell you get how much losses, and these losses are converted to heat usually. So if those areas coincide, if we have a cell where we get a lot of heat production from soiling losses, and that coincides with the same cell actually showing elevated temperatures in infrared, then this is a match, and we tell that watch out, user, that could be due to soiling, but it's not like a definite answer. It cannot be, because of course nobody can exclude that this same cell is actually defective. So that's possible in theory, of course, but we give that hint by just comparing the areas that are affected. So that's basically the principle. I hope that that answers the question.
Yes, thank you, Leo. Yeah. Okay, we have, I think, another questions. So I think it's a technical question for Fabian. How can I create an account to log into Volatec web app? So
yeah. Well, our service is actually commercial. So if we're talking about your own power plant that you want to scan, like on a grand scale, of course we need to talk about how to get that going. But we have a demo plant where you can click around our tool and explore all the tools and everything. And I can provide access to anybody. Just write me an email and you can get access there for free, because that's not it's nothing new. Okay.
Thank you, Fabian. So another question, I think, from Juan Lopez Garcia. I think maybe for Leo, I think. Do you think that cell technologies might have an influence in soil deposition? And if so, is there any model taken into account? Of course, technology, cells technology.
So I think, yeah, Alvaro gave a very good answer to that. More than the type of cell itself, again, the type of glass, the texture, and so on will probably have a role on the deposition, so on the way particle deposit and attach. Clearly, if the different cells are experiencing different temperatures, and there might be different temperature coefficients and so on, then probably also that deposition is different, but there is no evidence about that. So again, I think the main role there will be possibly played by the coating or the texture of the glass.
Okay, thank you, Leo. So I think I don't have any other questions from. Okay, I think a question from Delhush Mina from, I think, if I remember, Australia. Did you analyze, to Leo, of course, did you analyze how much dust particles were carried along by the dust storm during the weeks? I mean, there is a separate effect of aerosols already present in the atmosphere and not suspended on PV surface, which is called soiling. Okay.
Yeah, that's what it was the first presentation, you mean? And yeah, so that's what we did. We looked at the impact of the aerosols, not at the impact of soiling in that work. And again, we found that the aerosols themselves had a significant impact on the performance before even soiling built it up. So yeah, Again, for dust storms, you have to take into account about the concurrent effect, which is, again, the suspended dust, and soiling comes only after, and again, can prolong the effect of the dust storms even after the sky has cleared.
Okay, thank you, Leo. So a question that I have already asked in your first talk, I think, about clipping, and also I think the stabilization of the grid. Can we model this type of or predict this type of events in order to avoid that maybe cleaning can be costly?
So you're asking how we can model them?
Yeah.
So
if we
clipping
can
is,
model them.
yeah, clipping
Yeah.
is much easier to model. I remember Tore also showing that by knowing the configurations of your system, and again, the different sizes and the environmental conditions. Curtailment is much harder because again, it will depend on the grid, and sometimes the way systems are the grid decide to curtail some systems is not clear or publicly available. So that might be a bigger issue to handle and to model. So right now we can just work on, you know, aggregated numbers, but at system level, I'm not familiar myself with the way that that is handled. But yeah, clipping can be modeled.
Okay, thank you, Leo. I think we can invite Professor Ahmed Innawi to this panel in order to wrap up this morning event regarding the plenary and also this workshop.
I don't have any very much to say except to thank all the panel for this very important and very deeply done job through this workshop. And I think it's very important to, if the photovoltaic will be developed and the payback work, the soiling is very important. But I want to close with one very pertinent question, which is not really scientific, but very important, more political. You know that there is a war now in Europe where Europe is involved, Russia and Ukraine. And you know the destruction of building and destruction of the country will also include the destruction of panel or PV field, for example. And the energy is very important. If tomorrow we turn to the energy transition, 100% energy transition, every country has a PV field to be protected. And since we are talking about the protection in terms of soiling, we have also to think about the protection by law, in terms of law for the energy. This means for PV technology when we have the energy transition. What do you think? Is it possible to make law like for nuclear energy that if there is a war, no one is allowed to bombard like this the all energy field, for example? What do you think, guys? Of course, the
So
question.
very difficult, multi-layer question. I don't know, Fabian, you want to start? No.
Well, I mean, it's far less dangerous to have like solar energy as one of the pillars of your energy system in the grid, like far more resilient against destruction, of course, because we wouldn't want to imagine what happens if you bombard a nuclear power plant as opposed to a solar field, where for a solar field you'd need like thousands of bombs to destroy it completely, and it doesn't do much harm to the environment in the end, like not so much. But nuclear is, it's not an alternative in that respect. So I find renewables make you more resilient in terms of you're not it's not possible to also put pressure on the country, as it has happened to Germany with cuttings of gas supplies. So if you're more renewable you have, more independent you are, and more less it's less possible to put pressure on a country. So that's also one aspect where solar can help a lot. And we're all working on improving solar, so soiling comes into there. And I fully see this as a method to lower the risk of wars and conflicts in general, in my opinion.
I totally agree with that. I think as solar energy researchers, we are contributing to making our energy system more secure. That goes also through better understanding of performance and losses of the system. And again, contributing also to a more distributed systems, meaning that again, if the energy production is more distributed, there are less sensitive points and less risk of structural failures that might be induced by wars and so. And again, as Fabian said, by lowering the cost of energy, hopefully we are also contributing to improving quality of life, and thus, reducing conflicts between people and nations.
I'm rather thinking about United Organization law, that there are some new law for photovoltaics, for green energy to be protected. That's what I'm rather thinking.
The critical infrastructure, yes, of course.
That's what I'm.
Of course. Yeah, well, cybersecurity is, of course, crucial. I mean, if somebody logs into many plants at once, 4 gigawatts, I think, is the thing. If you cut off 4 gigawatts of any electricity production in the European grid, you would cause a blackout on a European scale, and that would be like really bad, catastrophic. Yeah.
Yes. Anyway, I think your workshop have brought a lot for our graduate students, for our scientists, and I really thank you very much. And I give the floor again to Alawi, if he want to.
Thank you, Professor. Thank you, Professor Ahmed Inawi. So I think we have arrived to the end of this session. I want to thank Professor Leonardo Micelli, Fabian, Alvaro, and also Thor for joining us today for this big events, as this issue of soiling is rising regarding the development of PV technology, and also the PV installations around the world. So thank you once again, and looking forward to meeting you in our next conference series.